So now we know how to encode LDPC codes. And to wrap up the chapter of LDPC codes, we're going to look at some examples of what kind of codes are being used in practical settings and in practical systems. So we looked at how to generate parity check matrices, but if you look at the parity check matrices that are in standards, you will see that they are still a little bit different. And we're going to see how we can construct the parity check matrices that are actually being used in practical code settings. So in practical standards and communication systems, usually a subclass of LDPC codes called quasi-cyclic LDPC codes are being employed. These quasi-cyclic LDPC codes, they have very appealing properties for implementation, and that's why they are being favored. And quasi-cyclic LDPC codes are a class of codes that allows us to reduce the size of the parity check matrix even further. So how are quasi-cyclic LDPC codes defined? But they are defined based on what is a cyclic shift of the identity matrix. So we define a matrix P, and matrix P is the identity matrix that we cyclically shift by one position. So we have the identity matrix, it has ones on the main diagonal. So now we shift this by one position. So I put the 1 in the main diagonal, one position to the right. Put the 1 on the second row in the main diagonal, one position to the right, and so on. And in the last, there would be a 1 here in the, so this 1 in the main diagonal would move to the right, but we cyclically shift the matrix, so it will move to the first column. You can think of this as wrapping the matrix around on a cylinder and then just changing the cylinder by one position, rotating the cylinder slightly, and then unwrapping the cylinder again. That's how you can think of this. So, and this is a matrix that we give a particular name, and we give this matrix a name P. And the matrix P has a size S times S, so it's a square matrix. And it has ones at the position I and I plus 1. So row 1, column 2, row 2, column 3, row 3, column 4, and so on. And it has a single 1 in position S1. So in row S, column 1. And everywhere else it is zeros. So essentially it's the cyclic shift of the identity matrix. That's the matrix P. Because it's so special, we give it a specific particular name. So essentially with this matrix P, we can use it to generate all the possible cyclic shifts of the identity matrix. So how can we do this? Well, if we take P to the power 0, that's the identity matrix. Something to the power 0 is 1. Same for matrix. A matrix to the power 0 by definition is the identity matrix. If you look at P squared, so it's P multiplied by P. And what P does, it essentially, if you multiply matrix by P, it cyclically shifts this matrix by one position. It's a cyclic shift of the matrix by one position, so it's a cyclic shift of matrix P by one additional position. So again, put the identity matrix on the cylinder, you rotate the cylinder by 2 positions, and you unwrap it. And that's this matrix P. So this is how you can actually get the different cyclic shifts of the parity check matrix. The identity matrix. So just by taking P to some exponent, this will give you some cyclic shift of the parity check matrix. Okay. So we also would like to have the zero matrix. So we introduce a special element. We give this element just a name. It's defined as the void element. So P to the power of void is the all zero matrix. That's just a definition that we do. So this is actually, we put a define sign. So this is a definition. So now we can specify a parity check matrix based on the exponents of the matrix P. So let's take a look at an example. So we define a base matrix B tilde. This base matrix B tilde is of size m prime times n prime. We have this base matrix size m prime times n prime. And it contains integer numbers in the range 0 to s minus 1, or it contains the void entry. So this specific symbol that we define to be void. And usually, if you look in standards, this void symbol is defined by an integer number that's outside of this range. So for instance, a -1. So -1 is defined to be equal to. So I have this matrix B tilde. And this matrix B tilde contains these integer numbers. And we can use B tilde to specify a parity-check matrix by replacing each entry that is not void by p to the power bij. So we have an entry bij. Then we just replace this entry by p to the power bij. And if we have a void entry, we replace that one by the zero matrix. It's a parity-check matrix of a quasi-cyclic LDPC code. And here you just need to store m prime times n prime small integer numbers, very small storage requirements. So, for instance, if we want to generate a regular DVDC LDPC code, then we specify such a base matrix of size dv times dc. So in this case, the dimension of the base matrix, we call it B tilde, is equal to dv times dc. And we get a parity check matrix of size dv times s times dc times s. So the number of check nodes is dc times, the number of variable nodes is dc times s, and the number of check nodes is dv times s. And k is then larger than dc minus dv times s. So the first thing we can see is a bound on the rank of the matrix. The rank of the matrix is upper bounded by 1 plus dv times s minus 1. So how can we see this? Well, we see this if we sum up the first s rows. So if we sum up the rows corresponding to this, we get a vector containing n ones. It's an all one vector. It's a vector just containing n ones. If we sum up these rows, it's a vector containing n ones. And the same holds for each of those rows. So any of the consecutive s rows gives us a vector that contains all ones, and therefore we have linearly dependent vectors. So that's why we have rank deficiency. So now what we can also see is that if we permute the rows and the columns of the code, that means we can change the positions, and we can cyclically shift the positions such that you have the identity matrices in the first row. So we have identity matrices in the first row and in the first column. This will not change the code. This is just a reorganization of the code bits and a reorganization of the parity check equations. So we have an equivalent matrix that has zeros in the first row, zeros in the first column, and then integer entries below. So essentially the degrees of freedom that we can choose from is dv minus 1 times dc minus 1. Okay, so this some properties. Let's take a look at an example. So here we have an example. We have the base matrix of our 3-6 regular LDPC code. So this is a 3-6 LDPC code. So we have the base matrix 0, 0, 0, and 0, so the identity matrices here. And then we have some of the shifts down there. And here we have the matrices with S equals 100. So we have this matrix P of size 100. So this is the identity matrix of size 100 times 100. And you can see that the dimension of H is equal to 300 times 600. And here you can see the cyclic shift. So this is the matrix shifted by 11 positions to the right. This is the matrix shifted by 21 positions to the right. The matrix shifted by 77 positions to the right, and so on. And the grids, they are used as visual guidelines to be able to distinguish the different blocks. So that's a very simple way of constructing regular codes. And essentially the storage requirement for this rather big matrix, they are pretty small because you just need to store 6 integer numbers. That's it. Actually, no, it's 10 integer numbers. So 5 plus 5, 10 integer numbers. And that's pretty simple. Here we don't have any void entries yet, but that's essentially what we have. So we saw in the previous chapter that we should avoid cycles of length 4. And we need to take this into account when selecting this shift values Bij. And we usually select the shift values such that small cycles are avoided, essentially such that cycles of length 4 must be avoided. And there is a very nice condition for checking if two particular entries of the matrix form a cycle of length 4. That's a so-called difference condition. So we have no cycles of length 4 if all combinations I1, I2 from 1 to dv, and they are different. So essentially we choose 2 rows of the parity-check matrix, and then we choose 2 columns, J1 and J2. And again, we need to do this for all possible combinations of 2 rows and 2 columns. Then we must have the condition bi1 j1 minus bi2 j1 plus bi2 j2 minus bi1 j2. This must be different from 0 modulo s. That's the difference condition. So let's look at an example from the previous slide. So I assume that this is I1, this is I2, this is J1, this is J2. So essentially what the condition says, and let me just copy the equation to the previous slide. And sorry for this red arrow. This is because I copied from the wrong window, but we can live with that one. So bi1 j1. So it means we start here, and then we go to bi2 j2, and we take the difference. Then we go to bi2 j2, and then we go up. So again, we look at this we look at such a square in the base matrix. And then we go around the square in a circle. So like we go down, we go left, we go right, we go up. So we go in a circle, and then we take the difference always. When we go down, we take the difference. When we go up, we take the difference. So here, this means that 77 minus 55 plus 21 minus 34, which is equal to 22 minus, this is 13, which is equal to 9, and this is different from 0 modulo S. So this means that here in those matrices, we will not have a fourth cycle. You can see this. You have a fourth cycle, you need to fulfill this row column constraint. So if you, for instance, go down here, you see that you will not form a fourth cycle because you will not end up. And you need to check this for all possible combinations here. So for instance, if you had one of those would be 0. So let's assume you have like a B tilde, which is 0, 0, 0, 0, 11, 11, 0, 11, 85, 0, 0, 4. That wouldn't work because here you have P1, J1 minus P1, J2, and this would be different from 0. This would be equal to 0 modulo S. So this wouldn't work, and this means you will generate 4 cycles. So this is the condition, and when you generate the matrix, you need to make sure that this condition is fulfilled for all possible combinations of I and J. And then you will avoid 4 cycles and you have a code without stopping cells of size 2. So the code that we just constructed is what we call an array code. And the drawback of this code is that the minimum distance is rather bad. So in this code, the minimum distance is upper bounded by dv plus 1 factorial. So this is bad because it means the minimum distance will not increase with n. And usually we want to have a minimum distance that increases with n. So increase n, would like to have a double. If we double n, we would like to have a doubling of the error correction capabilities. But here we have fixed error correction capabilities. So this is not necessarily good. And so we have rather bad minimum distance. However, usually it turns out that the weight distribution is not so bad. So this AD min, and AD min plus 1, they are usually small. So the performance can be acceptable for some applications, which is why these array codes are being used. How can we make the minimum distance larger? Well, by introducing void entries. So far we haven't used any void entries. By introducing void entries, we can improve the minimum distance properties. So that's why in general, we allow void entries to get more sparse base matrices. And essentially all practically relevant codes that we use today, they are based on these constructions. Also very nice property is if you change this parameter s, you can get different codes. If you want to have a smaller code, use a smaller s. If you want to have a larger code, you increase s. And this is usually foreseen by the construction that you can change the s and that you get different codes of different rates. For instance, this is being done in Wi-Fi, this is being done in 5G, and in many other systems. So we're going to look at a code, that's the WiMAX code of size 576 and rate 1/2. For those of you who don't know, WiMAX was a competitor to LTE. So it was a mobile communication system that was developed in the early 2000s, and it was foreseen to compete with LTE. In Europe, it wasn't widely deployed. It is still deployed in Africa, for instance. So there are WiMAX networks that are in use in African countries. But in Europe, it has lost against LTE. But it was a competitor of the LTE system that we still use today if we don't have 5G. So here is the code of that we have in WiMAX of rate 1/2 and with 576 bits. And this is the base matrix. So here we have the base matrix B tilde. And I don't show the void entries. So if there is a void entry, it's just being left empty. And this is the matrix that we have. We can see the first column has 3 entries. We have 3 entries. Then we have a column with 6 entries. We have another column with 6 entries. And we have some columns with 2 entries. And here we have a very particular structure. And this structure will help us encoding. So you can see this is very helpful for encoding. We're going to see this later. So the degree distribution is given here, so you can just count the degree distribution from the base matrix, and from L of Z and R of Z, you can get lambda of Z and rho of Z. Now, if we construct the parity check matrix, this is what we get, and this is a little bit too big, so we need to cut the matrix here. So this is the matrix H. The parity check matrix, and what we get is the matrix, and we can see that it's already in the form for encoding. If we take a closer look, we can put it into this form and go. Yeah, let me just redraw this. Here we go. So this is the matrix T. It's in lower triangular form. This is the matrix E. This is the matrix A. This is the matrix B. This is the matrix C. And this is the matrix D. So canceling E is actually pretty simple. It's just adding this row to this row. That will cancel E. And then you get a very simple C tilde. It's just this row plus this row. D tilde is just this row. And you can do the encoding actually in a very, very simple way using this very particular structure. And also the matrix T has this very special dual diagonal structure that further simplifies encoding. So actually don't even need to invert T because of the simplicity. You can do encoding directly by inserting, by solving the system of equations very simply. Okay, so this is the WiMAX code. So as I said, it's immediately in this form that we need to have. And actually there is a very simple circuit that you can encoding using accumulators and what is a circuit that is called a barrel shifter. And this class of codes also needs to very, very elegant and simple encoder and decoder implementations. So here's another example. This is the DVBS2 code. And again, sorry, there is change the slides. There was a mishap. So the matrix is look like this. So this matrix is rather big. It's 65,000. The circlets are very small, so you can see the circlets, you can see the grid. You can see it has the same structure as before. It has some special matrices that don't follow this rule. They have 2 circulants. These are marked in orange here. But all the other ones, they are just permutations of the identity matrix. You can generate this code in MATLAB. It has built-in command that is called DVBS2 LDPC. And however, if you look at the code that MATLAB spits out, it will not be in this form. So it will look, the matrix will look completely different. And that's why MATLAB has some permutation. And the way it is specified in the standard, it's specified after some permutation. But if you undo this permutation, then you actually get this circulant form. So this is something I did manually. I undid this permutation in order to get this circulant form. So this is the DVBS2 code that is also in that you can use inside MATLAB. So now we're looking closer at codes that have this special structure that we can use for encoding. So this one and this structure. And it turns out that this is something special because having this structure essentially violates everything we learned about LDPC code so far. So what we learned about LDPC codes was that we should have a random construction. Now, however, having this very specific structure, that's not random at all. Not random. So we need to take into account when analyzing and constructing the code that there is this special structure that we can use for encoding. And it turns out that these codes, they have a very particular structure, and these codes also have a particular name, and they are called repeat accumulate codes. And especially if we have many degree 2 variable nodes. So if we have many degree 2 variable nodes, and in particular, if the number of degree 2 variable nodes is larger or equal than 1 minus the design rate, then it makes sense to use this repeat accumulate structure in practice. And in particular, an LDPC code that has a repeat accumulate structure has a parity check matrix that looks like this. So we can write the parity check matrix H as consisting of a matrix H tilde that we concatenate by a matrix D, and D is this so-called duodiagonal matrix. D is a matrix that has ones on the main diagonals. The main diagonal is full of ones, and it has ones on the off diagonal. So this is the case of repeat accumulate. So here's an example. It's a parity check matrix of such a code. So we have here is a simple matrix with M equals 20 check nodes and N equals 60 variable nodes. So it's a code of rate 2/3. And we see that here we have this matrix D, and here we have the matrix H tilde. And here's the degree distribution of this code, and this is an example of a repeat accumulate code. So why are repeat accumulate code popular? Well, encoding is very, very simple. And let's take a look at why encoding is simple. So if we have a code word, we write the code word being X is U followed by the parity bits. So we put the information bits in the beginning, followed by the parity bits. And X is a code word if H times X transpose is equal to 0, which means that H tilde D times U transpose P transpose is equal to 0. So H tilde times U plus D times P transpose is equal to 0. This means that we could obtain P transposed as D inverse times H tilde times U transpose. But we can also solve the equations directly. We don't need to invert D, we can solve the equations directly. So how does this look like? So we start from this equation number 1. So D times P transposed is equal to H tilde times U transpose. And if we look closely, D times P, so D is equal to 1, 1, 1, 1, and so on, times P transposed, this is equal to P1, P2, and so on. So D times P transposed, this is equal, so the first entry is P1. The second entry is P1 plus P2. The third entry is P2 plus P3, and so on. So essentially, D times P transpose is a vector that has in the first coordinate P1, in the second coordinate P1 plus P2, in the third coordinate P2 plus P3, and so on and so on and so on. So we can say that P1, the first entry of this vector is P1. So P1 is equal to the first coordinate of H tilde times U transposed. And that is just the sum from j going from 1 to k of H tilde I j times Uj. Since it's the dot product of the first row of H tilde times U transposed. So take the first row of H tilde, multiply by U transposed, and that's what you get. That gives P1. So immediately can calculate P1 by taking the first coordinate of H tilde times U transposed. Then the second equation gives P1 plus P2. That's the second coordinate of D times P tilde, P transposed. That's the sum from j going from 1 to k of H2j times Uj. So it's the second coordinate of this vector that's equal to P1 plus P2. So P2 is equal to P1 plus the second coordinate. So you can immediately get the second coordinate like this. So you take the second coordinate of H tilde times U transpose, you add P1, and you get P2. So then that's the way of how to get all the coordinates. So we just calculate this vector. That's a simple because H tilde is sparse. And then you get P1, then you insert this to get P2, then you take P2, you insert it in the next coordinate, get it to the next coordinate to get P3, and you ripple through, and then you have the parity bits. A very simple way to get the parity bits and to do the encoding. So this is the general case. In general, Pi is Pi minus 1 plus the ith coordinate of H tilde times Uj. And the codes that we have seen, the DVBS2 code, the WiMAX code, they are essentially repeat accumulate code. So now how do we get the threshold of a repeat accumulate code? The threshold cannot be computed. So in theory, we could take this degree distribution and we could calculate the threshold of this degree distribution. And then we would see that the code will actually behave differently than this threshold. And that's because the code doesn't behave like this because it's not random. We assumed a randomized construction. We don't have this randomized construction here. So what we need to do is we need to take this special structure into account. So very important, the threshold cannot be computed with the method we have seen. We need to take into account the special structure of the code. And that's something we're going to do. So that's something we're going to look at next, and we're going to just stick to the binary erasure channel for the time being. So for this, we're looking at the degree distribution just of this matrix of H tilde. So assume that we have this matrix H tilde defining a code, and lambda tilde and rho tilde are the degree distribution of this matrix H tilde. Then R tilde is the check node degree distribution from node perspective. So then for the binary erasure channel, important, we're just going to look at the binary erasure channel, but we can extend this using Gaussian approximation to more general channel. So the iterative behavior XCL is given by this expression. It's epsilon times lambda prime times this guy, which has epsilon inside, which has R tilde inside, and it has rho tilde inside. And we have, of course, a dependency on XCL minus 1. So that's the iterative behavior of this repeat accumulate code. And if we compare this with irregular LDPC codes, this is what we had with irregular LDPC codes. So you see there is a significant difference between these two expressions. And therefore, the word of caution, the take-home message here is that if you have an LDPC code that has structure, they very often do not behave as we expect them to behave. LDPC codes with structure do not behave as expected. All right, so how do we get to this expression? This expression kind of falls from the sky. We're going to look at how to do this in a regular case, then it will become obvious of how we get to that expression. So we assume that H, we use a special case now. H tilde is a matrix that has a regular degree distribution. So it has a row weight of DC and a column weight of DV. And means we can obtain H by concatenating DV-DC regular LDPC code with the matrix T. So now the design rate of the code is given by DC divided by DV plus DC, or 1 minus DV over DV plus DC. Very good exercise for this is to show that this is actually the case. And you can do this again using a counting argument from graph. Just in a very similar way as we did for regular codes, just try by counting the edges. This will actually be the design rate. And the iterative behavior is given by the expression that we see here, which is just the simplification of the expression from the previous page by inserting lambda tilde, rho tilde, and r tilde. So let's look at how we can actually derive this. So we have our graph. Let's say we have a graph that looks like this. So we have the portion that belongs to H tilde. We have our variable nodes. They are erased with probability epsilon. And they are connected to some check nodes. So we have. So these are the connections to H tilde. I'm just going to draw some of those connections. So we have the erasure probability of the messages sent from variable to check node being C. We define this to be C. The messages coming from check to variable node, we define those to be equal to chi. And now we have this special structure. So we have extra check nodes, variable nodes, and essentially for each check node, we have one extra variable node. And then we have those connections to this extra variable node, this very special structure. So this variable node is connected to check node directly and the next check node. So it always connected to two neighboring check nodes. So we have this zigzag-like pattern. And of course, we could continue this pattern down here. So now we define messages. So the messages sent from the check nodes to those extra variable nodes, these are erased with probability mu. Because these check nodes, they are also erased with probability epsilon. And the messages sent from those extra variable nodes back to the check nodes, they are erased with probability eta. Okay, so now we can write down everything what we have. So we have, we start with Xi. So Xi, and let me use the blue color. So Xi is the probability that the message from variable node to check node is erased. And that is being equal to epsilon times chi to the power dv minus 1. So we have epsilon times chi to the power dv minus 1. So what is chi? So chi is probability that the messages from the check nodes to the left-hand variable nodes is erased. That is 1 minus, now we have DC minus 1 incoming messages from the left variable nodes. So it's 1 minus C to the power DC minus 1. And we have messages from the right variable nodes. So this is 1 minus eta to the power 2, because we have 2 messages that are incoming from the right variable node. So what is eta? Eta is essentially epsilon times mu. And what is mu? Mu is essentially 1 minus xc to the power dc times 1 minus eta. So we always cover the outgoing edge. So there's one outgoing edge that we don't compute. So it's just one incoming edge from this red variable nodes. So and from this, we can actually now calculate eta. So by inserting this expression here, so you actually get eta is epsilon times mu. So it's epsilon times 1 minus xc to the power dc times 1 minus eta. So this is epsilon minus epsilon times 1 minus c power dc plus epsilon times eta times 1 minus c power dc. And then we put everything that's part of eta on the one hand side. So it means that eta times 1 minus epsilon times 1 minus c power dc is equal to epsilon times 1 minus c to the power dc. So it means that we get eta being equal to epsilon times 1 minus c power dc divided by 1 minus epsilon times 1 minus c to the power dc. So and from this, we can actually calculate 1 minus eta, because we would like eta include here. 1 minus eta is actually put everything on a common denominator. So it's 1 minus epsilon, 1 minus c power dc times 1 minus epsilon, 1 minus c power dc minus epsilon minus plus epsilon times 1 minus c power dc. And this is cancel, so it's equal to 1 minus epsilon divided by 1 minus epsilon, 1 minus c power dc. So therefore, we can say that now we plug, we have 1 minus eta, we put this in here, and this will only depend on xc, this will only depend on xc. So we can say that c is equal to epsilon times 1 minus c to the power dc minus 1 times 1 minus epsilon divided by 1 minus epsilon 1 minus c to the power dc squared, and the whole thing to the power dv minus 1. So this is how you can extend the analysis essentially. Repeat, accumulate codes. So it's a little bit more complicated, but it's still something that can be done and that we have been doing and that we're doing. All right, so here you can calculate some thresholds of repeat accumulate codes. So this is being done in this Python notebook that we have. And we can see that the thresholds they outperform LDPC codes. And this is essentially because of this extra structure and this extra variable nodes of degree 2 that we have added here and that actually improve the threshold. Okay, so we can generalize this repeat accumulate construction, and the general way of these codes are so-called multi-edge type or MET codes. And what we have seen here is that we have different classes of edges that actually behave differently. If we go back to the analysis, we had this class of these edges, they behave differently than the messages that are being passed over these edges. So we have essentially two types of edges that each behave a little bit differently. And that means that these types of edges need to be analyzed in a different way than these types of edges. And this is something that we can take into account and essentially can use this for optimizing new types of code. Essentially, this multi-edge type construction is a generalization of irregular codes where we now put some very specific structure into the codes. And in general, the analysis is not too hard, but it turns out that optimizing codes is quite difficult. And we're looking at a simplification of this multi-edge type scheme, which is called Protograph-based code. So what does that mean? Protograph means we have a prototype graph. So prototype graph is an artificial word standing for prototype graph. And this prototype graph is a graph that describes the different multi-edge type codes. So this prototype graph is a graph that potentially has parallel edges. So here is a prototype graph. So we have 4 variable nodes, x1, x2, x4, 3, x4, and 2 check nodes. And we see that we have parallel edges here. So here we have 2 parallel edges, here we have 3 parallel edges, 2 parallel edges. Obviously, this is not an LDPC code. And we can construct an LDPC code using a so-called copy and permute operation. So that's something we're going to see soon. First, we can also describe the code using a proto matrix or prototype matrix. And this is essentially the adjacency matrix of the protograph. So it's very simple. It's the same way as generating parity-check matrix for an LDPC code. So it's a matrix of size number of check nodes times number of variable nodes. And the numbers in the proto matrix, they indicate the number of edges connecting variable node with check node. So for instance, we have a single edge connecting x1 with c1. So we're seeing one. We have 3 edges connecting x2 with c1. These 3 edges. And so on. So 0 edges connecting x4 with c1. So there's no edge here. So how does this copy and permute operation work? And we show that how we can construct the code. Again, we have a lifting factor s, and here we show it with s equals 4. So the first thing we do is we start with the protograph and we color the edge types. So each edge connecting a check node with a certain variable node gets a color, and if we have parallel edges, they will get the same color. We have different types of colors. So there's a green, there's a red, there's a blue, and so on. So we use different colors to connect the different edges. That's the first thing. First step we do. The second step, we copy the graph s times and put the copies next to each other. We replicate this protograph s times. And here we have now all the edges 4 times just next to each other. And we group the variable nodes that the 4 copies of the different variable nodes are always next to each other. And now the next step is we looking at the edges of the same color. So we pick edges of one specific colors and we apply a random permutation on the edges. And this random permutation is chosen such that we have no parallel edges anymore after the permutation. So for instance, we pick the green edges and we permute them like this. Then we pick the red edges and we permute them such that no parallel edges persist. For instance, like this. Well, it's very hard to see, but you can believe there are no parallel edges anymore. Then we pick these blue edges, we permute them such that we have no parallel edges, like this. Then the light green ones, like this. Then the orange ones and the light blue ones, like this. So this is an example. And now we have essentially a graph that corresponds to a parity check matrix. So we can get the parity check matrix from the protograph also. It's an equivalent operation. So we obtain the parity check matrix of size m times n by replacing each entry of the proto matrix by the superposition of Bij permutation matrices such that no one entries overlap. Very, very simple construction. And essentially, instead of cyclically shifted permutation matrices, we use random permutation matrices, and possibly we have superpositions of random permutation matrices. You can also do density evolution on the protograph codes. The thing we need to take care of is that each edge has different erasure probabilities because each edge type behaves differently. So we need to define Cij, the erasure probability of the edge computed by the variable nodes corresponding to edge type that connects Xj with Ci in the protograph. Kij is the erasure probability of the edge types connecting Xj with Ca in the protograph. And then we have the update rules that are given by this expression. Looks rather tough, but it's essentially it's pretty straightforward what is going on, and we can take a look at an example of why this works essentially. So let's take a look at an example. So let's assume we have a proto matrix B that is 1, 3, 1, 0, 2, 0, 1, 2. And that means that the parity check matrix H is equal to P1. We have P2 plus P3 plus P4. Then we have a P5, 0. Here we have P6 plus P7. 0 over here. We have P8 over there. And P9 plus P10. So that's the permutation matrices such that all entries are 1 or 0. So now we can draw the graph of this. We have 4 variable nodes, and we'll probably need a little bit more space. So let me just draw this. So 4 variable nodes, and we have 2 check nodes. So we have one edge connecting first one with the second, and we have a double edge connecting the first variable node, second check node. So this variable node is erased with probability epsilon. The message that we're sending from variable node to check node is erased with probability C11. So yes, so this one is erased with probability C21. So we have different erasure probabilities for the 2 different edge types. C11, that's the edge going from variable node 1 to check node 1. C21 is the one going from check node 1 to variable node 1 to check node 2. Then we have the second variable node has a triple edge connecting the first check node, which is erased with C12, probability C12. And all of the variable nodes are erased with probability epsilon. So then this guy is erased, connected like this. So we have erasure probability this is C13 and this is C23. And finally, we have a double edge connecting the last variable node with the second check node, which is erased with probability C24. And then very similarly, the message is calculated by the check nodes going to the variable nodes. This message is erased with probability chi11. This message is erased with probability chi13. And this one is erased with probability chi12. Then this one is erased with probability chi21. This one is erased with probability chi3. And this one is erased with probability chi24. So, and now we're just looking at what happens at iteration L. The iteration L, we have C11. This is equal to epsilon times chi1 squared. Why is this? So the outgoing message that we calculate here is obtained by covering the incoming message along this edge. So we are erased with probability epsilon, or we have two incoming messages that are erased with probability chi21. So the outgoing message is erased with probability chi21 squared times epsilon. Okay. Then we can calculate C21. So that is epsilon times, we have one incoming messages that are erased with probability chi11. One incoming message erased with probability chi11. And we have one incoming message erased with probability chi21. Only one, because we calculate one outgoing message, so the other one is covered. It's chi11 times chi21. Okay, and then we continue like this. So we have C12 that is equal to epsilon times chi12 squared. We have three edges that are connected. We calculate an outgoing message, so there are two incoming messages. So we have two that are possibly erased. So then we have C13 that is equal to epsilon times chi23. Then we have C23 that is epsilon times chi13. And then finally we have C24 that is equal to epsilon times chi24. That's what we have from the variable node side. Now we're looking at the check nodes. So the check nodes, so we have chi11. That's 1 minus. Now we have one incoming edge from this side, but this one we cover. We don't look at this. Then we have three incoming messages from this side. It's 1 minus 1 minus C12 power 3 times 1 minus C13. That's the message coming from here. Then we have chi 1, 2. We have 1 minus C11. We have one message coming from the first variable node. Here we go. Now we have two messages coming from the second variable node because we need to compute one outgoing message, so we cover one. It's 1 minus C12 squared times 1 minus C13. Finally, we have chi13 and 1 minus C11 times 1 minus C12 cube. That's it. Now we can go for the second check node, and here the weight was essentially the same. So chi21 is equal to 1 minus C23 times 1 minus C24 squared. Chi23 is equal to 1 minus C. Sorry, I made a mistake. But let's take a look at the first one again. So we have two messages coming from C, from variable node 1. We need to cover one, and we calculate one outgoing message. So it's 1 minus C21 times 1 minus C23 times 1 minus C24 squared. That's it. Now we have 1 minus C. For the second one, we have 1 minus C21 squared. So we have two messages coming from the first variable node, and we have two messages coming from the fourth variable node. And finally, we have chi24, which is 1 minus C21 squared times 1 minus C23 times 1 minus C24. So that's it. And now we can say decoding is possible. So when can we decode? So if the limit, when the number of iteration goes to infinity, of C ij is equal to 0 for all possible combinations of I and j. So if all these coupled equations, so we have a coupled equation, we have 6 different x's, we have 6 different chi's, and they are coupled with this system of equation. And now we just update this, guys. Of course, here we always put an iteration counter, and this would be iteration counter L minus 1, but for keeping notation simple, we leave it. Now we evaluate these coupled equations, and if these coupled equations will eventually converge to 0, that means that the code is able to. So that is what we call a Protograph-based LDPC code. Okay, so we can also describe and repeat accumulate code as a protograph code. So an example of a 3/9 repeat accumulate code is a code that looks like this. So essentially, we have one of those, we have one variable node that is connected by a double edge to the check nodes. All the check nodes are the same, and we have this double edge that connects to the check node that will give us a repeat accumulate code. So this protograph-based codes, they encompass repeat accumulate code as a special case. So with this, we have seen some code constructions, and next week we're going to look at a very specific construction which is called spatially coupled LDPC codes that are further improving the code ensemble somewhat further. So with this, thanks a lot for listening and see you in the next week.